Hi guys, it's Mrs. Allison. So today we are going to talk about these tests. These are tests that we can use to determine if a series converges or diverges. And it's all based on the idea of limits to infinity, which is going to help us review for our Unit 5 test. So here we go. We're going to look at some of these tests. There are 3 tests we're going to focus on today. This chapter we actually have quite a few. But we're going to start today with the nth term test, move on to the integral test, and then finally on to the p-series test. So let's go ahead and get started. The nth term test. Here is one thing I want you to to highlight, to make note of. I don't know what you need to do to it, but the nth term test is specifically for divergence, only for divergence. And here's what it says. It says that if the limit as n approaches infinity of some function is not equal to 0, then we know for a fact that the series diverges. Okay, so if it's not equal to 0, the series diverges. Now here's the kicker on this. It is not okay to say that if the limit does equal 0, then the series converges. That's false. We don't know that. It may be true, it may not be true. But we can say for certainty that if the limit is not 0, then it for sure diverges. Okay? I'm going to start the problem and then I want you to do some thinking about it and then try the next one. But here's what this says. If we're going to use the nth term test, and not all functions can do this. Some work really well for this, and some do not. And we'll start to see when to use each test. But for now, this example one is all nth term. What I'm going to set up is I'm going to set up the problem, the limit as n approaches infinity of the function 5n squared plus 3 over 2n squared. So this goes back to what we did last unit. So I'm trying to find the limit to infinity. Well, hit pause and see if you can find that limit. All right. Hopefully you got done and you noticed that the limit of this is 5/2. Why? Because we have the same degrees in both the numerator and the denominator. This plus 3 is really not going to impact it much. So when we're talking about infinity, so I just compare the ratio of the leading coefficients, and my leading coefficients are 5/2. So therefore this limit is 5/2. Now what does that tell me? I know 5/2 is not equal to 0. So I can say that this series diverges. I can say that because it's not equal to 0. Okay, try the next one. So hit pause, try the next one and see what you get. All right, hopefully when you set up this problem, we get the limit as n approaches infinity of 4 to the n over 5 to the n plus 1. It looks like that plus 1 is all there. Now here's the problem. When I compare these aren't powers. And this 4 to the n grows just a tiny bit slower than this 5 to the n. So we're going to say that it's bigger in the denominator and therefore this goes to 0. And so what we can say is that we know nothing. We can do nothing with this from the nth term test. That doesn't mean there's not an answer. We just know nothing from the nth term. All right. Can you think of another way to look at this? Hopefully you remember our discussion of series and can say, all right, well, let's rewrite this. Let's rewrite this as 4 to the n over 5 to the n, 5 to the first. Or let's rewrite this as 1/5 over 4 to the n, 5 to the n. Or maybe we even take a shortcut from that, and I'm going to go ahead and erase this n and n, and I just rewrite the whole thing to the n power. What form is this in now? Hopefully you notice this is geometric. This is geometric, and therefore I know my r is 4/5, And I know that that is less than 1. So therefore, we can say that this converges. We can't say that because it's equal to 0, it converges. That's not that we can't make that statement. But I can say because it's geometric, it converges. So, in a situation where you're taking a test, you've got to make the choice as to which test makes the most sense. In this case, nth term didn't get me anywhere. Sure, try it, but it didn't get me anywhere. So I move on to geometric. All right, let's talk integral test. Okay, so the integral test allows us to compare a series to its integral in order to prove convergence or divergence. Now, there's 3 things that have to be true. In order for this to work, the 3 things that must be true: it must be continuous, it must be positive, and it must be decreasing. So in order to use the integral test, these 3 things have to be true. Now, here's what we can say. I can use the idea that if the integral from 1 to infinity of f of x is convergent, then the series is convergent. Or if the integral from 1 to infinity is divergent, then the series is divergent. Okay, so let's apply the integral test to see if these series converge or diverge. So the first thing I want to look at, is it continuous? So I'm going to start with the idea of continuity. Well, if I look at this first problem, what would make it not continuous? Hopefully you would notice it would be something in the denominator or something making the denominator 0. Well, is there anything that I can plug in that will make this denominator 0? The answer is no. So I know it's continuous, so we're good there. Now I need to check that all of the terms are positive. Well, again, this is all dependent on this lower bound to my upper bound. So if I'm starting at 1 and I'm moving to infinity, will all the terms be positive? Meaning, can I plug in a number between 1 and infinity and make this fraction negative? And the answer is no, I cannot. The last thing I need to check is decreasing. Now, this one can be a little bit funky to think about. But to be decreasing, think about like if I plug in 1, I would have 1 over 1 squared plus 1, so I'd have 1 over 2. If I plug in 2, I would have 1 over 2 squared plus 1, which would be 1 over 5. And if I plug in 3, I would have 1 over 10. Are these fractions getting smaller? If the answer is that they're getting smaller, then it's decreasing. So this is continuous, positive, and decreasing, so I can use the integral test. Here's what the integral test looks like. It says, find for me the integral from 1 to infinity. Notice it's the same bounds that we had in the problem. Of 1 over x squared plus 1 dx. Now I did change the variable to x, but that's only because we tend to know x better, or it was really just a mistake on my part that I didn't realize it was n, and it's okay, totally fine. So the problem is, this is what kind of integral? Well, notice my upper bound is infinity, which means it's an improper integral. So I'm going to go ahead and rewrite it. The limit as b approaches infinity of the integral of 1 to b, 1 over x squared plus 1 dx. Okay, first thing I need to do is anti-differentiate. Well, in doing that, I notice that this happens to be the arctangent, and this is the arctangent of x evaluated from 1 to b. So I'm taking the limit as b approaches infinity of, using the fundamental theorem, I would have the arctangent of b minus the arctangent of 1. Okay. Do we know the arctangent of 1? Meaning, what angle gives me a tangent that's 1? Hopefully you said pi over 4 on that. So this piece right here is just pi over 4. There's no, b doesn't impact this problem any, so it's just minus pi over 4. Now what about the arctangent of b? If I take the limit as b approaches infinity of arctangent of b, what this is saying is, what is the angle of tangent that gets me to infinity? Hopefully you can picture your tangent graph. thinking about what our tangent graph might look like, we know the tangent graph looks something like this with these vertical asymptotes. And the angle that takes me as close to infinity as I can possibly get is going to be pi over 2. And I'm going to be subtracting the pi over 4. And pi over 2 minus pi over 4 is pi over 4. Well, here's what that tells me. If I get a value here, meaning my integral converges, if my integral converges, then so too does the series. The series converges as well. And so therefore, I would say this whole thing converges. Both the series and the integral converges. So, hit pause and try example 2b. All right, hopefully you ran through your checks first. Continuous. Yes, this is continuous. There's nothing in this problem that's going to make it not continuous. Positive, it is also positive because every time I plug in a number from 1 to infinity, it doesn't mean all numbers, 1 to infinity only. Those are all positive. And decreasing, is this decreasing the whole way? And the answer is yes. And if you're not comfortable with that, check a few numbers. We would get 1 over 2, we'd get 2 over 5, we would get 3 over 10, and those numbers are getting smaller and smaller. Those fractions are getting smaller and smaller, so it is decreasing. All right, so we are going to rewrite this problem as the integral from 1 to infinity of x over x squared plus 1 dx. Now, that's an improper integral, so I'm going to write the limit as b approaches infinity of 1 to b, x over x squared plus 1 dx. Well, I can't integrate this one the way it's written, so I'm going to go ahead and use a u substitution, and I'm going to let u be x squared plus 1. So du would be 2x dx, which means we get 1/2 du equals x dx. And now I can make my substitution. I'm really going to be doing, I'm going to scroll up just a little bit. I'm going to be doing the integral, 1/2, the integral of 1 over u du, which means I get 1/2 the natural log of the absolute value of u plus c. I don't need the plus c because I'm about to do a definite integral here. So really this problem says the limit as b approaches infinity of, I've already done the integral work, 1/2 the natural log, remember u was x squared plus 1, and I need to evaluate that from 1 to b. So I've got the limit as b approaches infinity of 1/2 times the natural log of b squared plus 1 minus 1/2 the natural log, the absolute value of 1 plus 1. Okay, so this piece I get negative 1/2 the natural log of 2. I don't really need the absolute value in that case. But I'm still taking the limit as b approaches infinity of 1/2 times the natural log of the absolute value of b squared plus 1. Here's the problem. If I plug in infinity to the natural log, what do I get? Eventually I get infinity. And if this goes to infinity, this expression right here goes to infinity, it means that this whole thing diverges, which means that my series also diverges. So all I'm doing with my series is proving using an integral that I know or that I can find that the series diverges, because if the integral diverges, the series diverges. That's the integral test. All right, let's move on to the p-series test. The p-series says this. If you have a series in the form of 1 over n to the p power, where p is a positive constant, then this is called a p-series. So 1 over 1 to the p power, plus 1 over 2 to the p power, plus 1 over 3 to the p power. So keep in mind that this n is the values that we get from our series, and this p is some positive constant. We don't know what it is, but it's a positive constant. Now, there is a special case, and it's not necessary to know the name of the special case particularly, but you may see it come up. If P happens to be 1, so we have 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 plus 1 over, you get the idea. That's called a harmonic series. So that's the definition of a p-series. Now, there is a p-series test. And the p-series test has 3 parts to it. If we have a series in the form of a p-series, what we say is that it will converge if p is greater than 1. If p is greater than 0 but less than 1, it diverges. And if p equals 1, it also diverges. Yes, I could have combined these two. But if p equals 1, or is the harmonic series, then it diverges. So let's look at some examples of p-series, because oftentimes p-series are not actually written to look just like that. We may have to do some math to simplify them. So for example, on this first one, I gave you a hard one on the first one, because it doesn't really look anything like a p-series. So the first thing I'm going to do is I'm going to rewrite this, and I'm going to rewrite it using powers. This would be 1 over n times n to the 1/2. Now, if I remember my exponent properties, then I can rewrite this yet again, and I can rewrite this to say that this is the series from 1 to infinity of 1 over n to the 3/2 power. When I'm multiplying common bases, I add their exponents. And then this is a p-series. This is a p-series where that p-value, in this case, is 3/2. So since p equals 3/2, and we know 3/2 is greater than 1, we can say that this series converges. Okay, hit pause and try the next few examples and see what you get. All right, hopefully after rewriting some of these, like for example, b, oops, that's supposed to be an equals, that says minus, equals 1 to infinity of 1 over n to the 1/3 power. And if I look at my p-value here, my p-value is 1/3. And so if p is 1/3, the problem is 1/3 is less than 1, and therefore this series diverges. Okay, how do we do? Let's move on to C. We're going to use the same, I put a minus there too. I must have copied and pasted. So I'm going to rewrite this. This is the sum from n equals 1 to infinity of 1 over n to the 1/4. We see our p is equal to 1/4, and therefore this whole thing diverges. Now, this next one, hopefully it stumped you a little bit. Because if I go to rewrite this, I get 1 over e to the positive n. That's what that negative exponent does. It flips it. It makes it 1 over e to the positive n. This is not a p-series. Oops, p-series. It's not a p-series problem. But it is a problem we can solve. This is geometric. And in this case, my r is equal to 1 over e, which we know is less than 1, and therefore this converges. So, hopefully you start to see the pattern. P-series has my variable in with a positive constant exponent, whereas geometric has the variable as an exponent, so they're a little bit different. All right, so we've seen the nth term test, the integral test, and the p-series test. Obviously, 3 unique tests to be able to tell if a series converges or diverges. All right, that's all I have for you. You have a worksheet for an assignment, and we will see you soon.